time dilation and length contraction going to be the topics of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now, in the last lesson, we introduced the special theory of relativity, and we learned that the speed of light in a vacuum is constant. It has the same value in all inertial frames. And because of this, it turns out that time and distance have become relative, depending on what inertial frame you're in. And that's the topic of this lesson. We're going to find out that for observers that are moving very fast, some significant fraction of the speed of light, time appears to slow down, time dilation, and distance is measured seem to have a smaller magnitude, length contraction. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So we're going to start this lesson off talking about time dilation. And here's the lovely equation for time dilation. It turns out you can also write it in terms of what's called the Lorentz factor gamma here. And there's what the Lorentz factor is equal to. So, and then here's the formula for length contraction. You can also write it in terms of that Lorentz factor as well. Now we're going to spend a little bit of time early in this lesson deriving these expressions. If you're not on the hook for deriving them and just need to do some plugging and chugging, then you can probably skip past the first segment of this video. So, but it will be instructive to kind of give you an understanding of why time dilation and length contraction happen. Now, I've got a baseball here, and you might be wondering, why is Chad holding a baseball here? So, well, one, because baseball is the best sport that exists. And if you disagree, you're just simply wrong. So, but two, it's going to illustrate a point. So, velocity is constant when we're talking about the speed of light, but that's not normally our everyday experience for anything else. Velocity is not constant. And so if we see an object taking two different paths, and that's what the baseball's for here. So if I just throw this baseball straight up and straight down, well, right now, you, from the viewpoint of the camera, and me are in the same inertial frame. We're not moving. So relative to the Earth right now anyways. So, and it just appears this ball goes straight up and straight down. But if I come off to the side here and I start moving in this direction and then throw the ball up, well, we see two different things. From my perspective, in which I'm now in motion, it still looks like the ball's just going up and going down. But from your perspective, you viewed this as two-dimensional motion, as projectile motion we viewed earlier in the semester, early in the, I guess in the year. So, and you saw a parabolic path traced out by the baseball, so which has a different distance associated with it. And so normally the way we'd account for this is that, you know, I threw up the ball and caught the ball at exactly the same time, whether you look at it from your point of view or my point of view. And so we'd adjust the fact that the distance is different for those two paths. Mine just looked like it went straight up and down, yours along a parabola. And we adjust for that by adjusting the velocity. In my view, I just saw it as a one-dimensional problem, up and down. It only had a vertical velocity. But from your perspective, it had both an x component and a y component to its velocity, and it was the velocity that was different. And so in order to keep time constant, if the distance changed, the velocity changed. But with the speed of light, it's different. It's the velocity of light that's going to remain constant. And so if the distance is going to change, it is the time that's going to have to change instead. So that's kind of the basis of time dilation here. So now we're going to take a look at a little thought experiment that Einstein took a look at. And we're going to have a man on a train, and he's going to have a little bit of a light clock, is the way we often look at it. So, but ultimately he's going to have right at the center of the train car, there's going to be a light that is pointed vertically straight up. So, and when triggered, it's going to shine a pulse of light, maybe it's a laser, straight up. And then there's a mirror on the ceiling that it's going to reflect straight back down. So, and built into the light is also a detector that picks it up. And so we have two events here. We have the shining of the light, the pulsing of the light in the upward direction. So, and then when it hits the detector after it's been reflected back down, and we're going to measure the time between those two events from two different inertial frames. And one of them is just the observer right here. And from his perspective, so he just views the light going straight up and straight down. The problem comes in the fact that this car has a velocity v moving to the right. So, and as a result, if there's an observer standing on the ground that's stationary relative to the train, so the path they see that this light take is going to be different, and therefore the time's going to have to be different as well, since the speed of light is the same in all inertial frames. All right, so we want to define this time for this guy right here, and for this guy right here, so delta t is just going to equal distance over velocity, and that distance is just the height of the car, which we're going to call capital D here, times 2, because it's that way up and that way back, and that's the path of the light. So, and then it's all over velocity, which is the speed of light. So 3.0 times 10 to the 8th meters per second. But then we also want to look at what this might look like for this observer right here. And for that observer, things are going to be just a little bit different. And if we take a look, so what we're going to do is we're going to have this train car moving to the right with velocity v. And we're going to get 3 snapshots here. The one is where the light is fired. The one is where it hits the mirror and is reflected back out. So, and then where it's, after being reflected, detected by the detector back at the bottom. And those are the 3 points we're going to see here. So let's trace those out in red. So where the light is fired, where it's reflected off the mirror, so, and then where it hits the detector back. And we can define this time in 2 different ways. One, we can just look at the velocity of the train. If we say that this, the distance the train has traveled from where the light is fired and where it hits the mirror is a length L, and then from where it's reflected and back to the detector is another length L, then we could say that the time, so it would equal the distance over the velocity, in this case, in regard to the velocity of the train, and the distance traveled here is just 2L. So, and the velocity is just defined as v here. And so we could define the time in that perspective as well. So, okay, now this time is going to be, again, from the stationary observer's perspective. This time right here is going to be from the observer on the train. Now, it turns out we need to define one of those as, so what we call the proper time. So, and if you look on your study guide, which I don't know where I put that thing, found it. So if you look at your study guide, proper time is defined as the proper time between 2 events as measured from an inertial frame at rest relative to both events. So if an observer views both of those events as happening at the same location in space relative to them, that's the key. So if we look at the stationary observer, so the firing of the light, the pulsing of the laser here, if you will, so that's the first event. And then it's hitting the detector, that's the second event. And for this guy, it happens on his left over here, it happens on his right over here. Those are definitely not the same 2 locations. That is not proper time. As he sees time here, that's not going to be defined as proper time. But for the guy on the train, it happens right off to his right, and it happens right off to his right. And relative to his position, so both of those events happen at the location in space relative to him. It's he who is measuring proper time. And so in this case, we label this either delta TP or delta T naught, depending on which textbook you might happen to be using. And so it's his measure, he's measuring proper time. And how we define proper time, so at least from whose perspective, and proper length, when we get to length contraction, is super important and one of the biggest sources of confusion. So just keep that in mind. So it's the observer on the train for which we have proper time here. So we want to take a look at this time from the stationary observer in one other perspective here. So if we look, just like the baseball, when I threw it up, it looked like it was going straight up and down as I walked across your screen, but for you, it looked like it had this parabolic trajectory. The same thing is true of the light here. For the guy in the train who's moving with it, it just looks like it went straight up and straight down. But from this guy's perspective, so it pulsed, started right here, and then it traveled along a diagonal to where it was reflected, and then traveled along a diagonal to where it hit the detector. And that's the path the light took there. And that's a longer path. So, and because it's a longer path, because the speed of light is fixed, it's going to be a longer time as well, as we'll see here. So we got to figure out how long that path is. Well, we can draw a right triangle here. So we can see that this is the hypotenuse of the triangle here. That's half the path, and then the hypotenuse of a similar triangle with the other half of the path. So this leg of the triangle is L, and this leg of the triangle right here is D. And so we can see that this is going to equal the square root of D squared plus L squared. So for solving with the Pythagorean theorem. So that's half the path. The whole path would be double that. And so from this guy's perspective again, take a look at this, and then delta T. So, and again, this is still his perspective, not the guy in blue here that I've highlighted in blue, but I need a lot of room on the board here, so I'm writing it over here. So we wrote it from the standpoint of the train. Now we're going to write it from his standpoint, the stationary observer. And in this case, it's 2 times that square root of D squared plus L squared all over the velocity, which is the speed of light. And so really, these are both the same expression for time, one expressed in the path and the speed of the light, one expressed in the path and the velocity of the train. But we're going to use them both. Ultimately, we're trying to get to an expression that writes the delta t in terms of delta t proper and just in terms of the velocity of the train, so and the speed of light. So keep that in mind. All right, so in the end, we don't want D and we don't want L to show up in here at all. And so first thing we do is get rid of L. And if we rearrange this expression right here, L is going to equal V delta T over 2. And we're going to substitute that right in here for L. And so we're going to end up with delta T equals 2 times the square root of D squared plus V delta T over 2 squared all over C. So real easy to get caught up in the weeds here. So what we now want to do is get rid of this square root right here. And to do that, we've got to get everything else on the other side of the equation. And so in this case, we'll multiply it by C and then divide by 2. And we're going to get C delta T over 2. So it's going to equal the square root of D squared plus V delta T over 2 quantity squared. And now that I've got the square root by itself, effectively what I'm going to do is square both sides of this equation. Well, when you square square root, you're just left with what was under the square root. But on this side, we're going to be left with C delta T over 2 quantity squared equaling D squared plus V delta T over 2 quantity squared. All right. From here, we want to go through and solve for delta T once again, get a new expression for delta T. And to do that, we've got to get all the terms that have delta T in them off to one side of the equation. So I'm going to subtract this term over to the other side, and we're going to end up with C delta T over 2 quantity squared minus V delta T over 2 quantity squared equals D squared. So the next thing we're going to do is factor out a delta T squared out of both of these terms. And so in this case, if we do that, we're going to have delta T squared, and then we're going to have C over 2 quantity squared. So minus V over 2 quantity squared. So, and then equals D squared. All right, we're getting closer. Now we want to solve for delta T, so we're going to get delta T squared by itself, divide by this term over here to the other side, and we're going to get delta T squared equals D squared all over C over 2 quantity squared minus V over 2 quantity squared. Now there's a couple things we can do with this. So one, we can expand this out. This is really equal to C squared over 4 minus V squared over 4. And in fact, I'm going to substitute that right back in because it might be a little easier to see the next step if I do. So this is really C squared over 4 minus V squared over 4. And so I can factor out that 4 now as well and have 1/4 C squared minus V squared. But dividing by 1/4 is the same thing as multiplying by 4. And I can get rid of having a fraction in the denominator by doing so. So we're doing this for a reason. I lost my minus sign somewhere along the way. But we're doing this for a reason. So we want to get an expression that we can take the square root of. And if you notice, though, you're starting to see where we might have a V squared and a C squared under a square root in some way, shape, or form. So to get there, now what we want to do from here is actually divide the numerator and the denominator by C squared. So I'm going to divide by C squared here, and I'm going to divide both of these terms by C squared here as well. Now, because I divided both the numerator and the denominator by the same factor, I haven't changed the overall value of what's on that side of the equal sign, as long as I do both. So that's going to work. And in this case, though, you can see that C squared over C squared is 1 minus V squared over C squared, and this is starting to look rather familiar here. And so what I'm going to do from here is take the square root of both sides so that we can solve for delta T. And so in this case, we're going to get delta T. So square root of 4 is 2, square root of D squared is D, square root of C squared is C. So, and then I could look at this as being either all over this, or I could look at it as times 1 over the square root of 1 minus V squared over C squared. I could say that's the square root of everything under there, or the square root of 1 is really still 1, and that's why I can write it like this. And we're just about there. So if you notice, this looks a whole lot like what we got right here with one big exception. We've got this 2D over C. But 2D over C is how we defined proper time just a little bit ago. And so all of a sudden now, we can substitute that in and get delta T equals our proper time. And ultimately, we can now write it as over the square root of 1 minus V squared over C squared. Cool. And again, that factor 1 minus, or 1 over, I should say, the square root of 1 minus v squared over c squared, that is gamma, which is why we can write this as delta t equals delta t proper times gamma as well. That is your derivation for the Lorentz factor. So, and keep in mind that because distance equals velocity times time, well, in our case, we're going to look at it as length equals velocity times time. And so there's a relationship between length and time. So, and ultimately that's where we come up with this lovely expression in similar fashion. We're just using the time we've solved for here to solve for a length. And then we're going to redefine what's called the proper length yet again. Unfortunately, you're going to think it's kind of assigned a little bit backwards. So if you look on the study guide here, and I'll make sure this gets up on the screen, but proper length. So we talked about how proper time was defined, and we decided it was defined for the observer that was on the train, because the two events, that the starting point for where we're measuring time and the ending point for where we're measuring time, happened at the same location relative to him. Okay? Well, proper length is the length between 2 points as measured from an inertial frame at rest relative to them. And so in this case, it leaves the detector at this location in space. So it arrives at the detector at this location in space. So which observer is at rest is exactly positionally related to both those points at the beginning and at the end in exactly the same way. Well, it's this guy now. He's the guy that's at rest relative to that point and that point. His relationship to that location in space and that location in space does not change. It's for him that will actually define proper length when we get to length contraction. So I just wanted you to see there's kind of a little bit of a difference here. It's this observer for which we observe proper time, but it's this observer for which we observe proper length. It's super confusing. That's one of the most confusing parts. So we'll do a couple practice problems here in a little bit though, so you can see the difference. So here's the first problem we're going to do. The question says, Proxima Centauri, our nearest neighboring star besides the Sun, is 4.2 light years from Earth, as measured by an observer on Earth. If a spaceship traveling 0.90 c, that's 0.90 times the speed of light, travels to Proxima Centauri and back, how long is the journey from the perspective of an observer on Earth and from the perspective of an observer on the spaceship? What is the distance of the round trip from the perspective of an observer on the spaceship? Now notice the question doesn't ask what is the distance from the perspective of somebody on Earth, because we can kind of really easily see that. So there's 4.2 light years. Don't get confused, that is not a measure of time, that's a measure of distance. A light year is the distance light travels in 1 year, so 4.2 light years would be the distance light travels in 4.2 years. And so this distance, if we're going there and back in the spaceship, the distance from the perspective of somebody on Earth is just 8.4 light years. And that's why it wasn't asked. It would be a simple thing to calculate here. But we do want to know what is the distance, so as measured by the guy on the spaceship here. And you might be like, Chad, that's a spaceship? Yes, that's a spaceship. According to my artwork, that is a spaceship traveling at a velocity of 0.90 times the speed of light. But then we also want to know how long is the trip from both of their perspectives. So, and again, one of these will take into account that time dilation. My first question is, for whom do we associate proper time? And again, if you recall what proper time was defined as the time between two events as measured from an inertial frame at rest relative to both events. So here we're going to kind of break this up into 3 events here. We're really going to or at least 2 sets of events. So we're going to talk Earth to Proxima Centauri. So, and for the guy on Earth, the departure of the spacecraft on Earth, or from Earth, and then arrival at Proxima Centauri definitely takes place at 2 totally different locations in space. But for the guy on the spaceship, so he's on his spaceship. Both these happen effectively right outside his spaceship. So when we leave Earth and when we arrive at Proxima Centauri. And then for the return trip, it's just the same thing in reverse. We start at Proxima Centauri as the beginning of the event, and then arriving back at Earth as the end of the event. And again, for the guy in the spaceship, those both happen right outside his spaceship, right outside his inertial frame. It's for the guy on Earth that it's different. And so it's for the guy on the spaceship that we would define the proper time. For the guy on Earth, it is not the proper time, but will just be plain old delta t in our equation for time dilation. Now, a couple other things. If he were actually traveling at the speed of light, then we'd know exactly how long this would take based, relative to the observer on Earth. It would be 8.4 years, because it's an 8.4 light year distance. So if he was traveling at exactly the speed of light, not 9/10 of the speed of light, but exactly the speed of light, then it'd be an 8.4 year journey. So in this case, then we can figure that out and say that delta t, so in this case, is going to be distance over velocity. So which in this case, that distance is that 8.4 light years, which I'll just abbreviate as Ly. and the speed he is traveling is 0.9 times c. And we can look at this a couple different ways. You could look at it 0.9 times 3.0 times 10 to the 8th meters per second, and that would be true, and we'd have a major units problem. Or we could look at it as 0.9. So a light, I should say the speed of light could also be looked at instead of 3.0 times 10 to the 8th meters per second. You could look at it as 1 light year per year. And so in this case, if it's 0.9 times that, it's going to be 0.90 light years per year. And look at it that way, because now we don't have our units problem. And the light years part of it and the distance is going to cancel. And when you divide by 1 over years, you're going to get an answer in years. And so here, delta t from the perspective of the observer on Earth, we don't need any crazy relativity calculator or equations to solve for this, but it's just 8.4 divided by 0.9. And it's going to be 9.3 years to 2 sig figs. Which makes sense. If he were traveling the speed of light, we would have known it would have taken him 8.4 years. Since he's traveling just a little bit slower, it should take him a little bit longer, again, as viewed from an observer on Earth. Well, what about then this guy here? How long does it take him? And that's what this equation's for. So if you notice, we have to actually rearrange it. We have delta t. We're going to solve for delta t proper in this case. And so in this case, we're going to end up with delta t, and we'll multiply up by this on the other side. So it's going to be delta t times the square root of 1 minus v squared over c squared is going to equal our delta t proper. All right, let's do some plugging and chugging here. So here we've got delta t was 9.3 years times the square root of 1 minus 0.9 c squared over c squared. Well, 0.9 gets squared and the c gets squared and the c's cancel, but you're going to end up with 0.9 squared. And so we got 1 minus 0.9 squared, and then we'll take the square root. And so in this case, we got the 9.3 times the square root, and then I'm going to use a parentheses, 1 minus 0.9 squared, and I'll close my parentheses, and actually I'm going to make that 0.90 squared. I know that doesn't change anything now, but it'll allow me to make my answer for the next problem preemptively a little bit easier to substitute in. All right, and this is going to get us 4.05, so 4.1 years rounded to 2 sig figs here. And again, that's our measure of proper time. And so from the guy on Earth's perspective here, it looks like time is passing more slowly for this lovely guy here. And this is kind of the nature of the twin paradox, where if you had 2 twins on Earth and one goes on a journey on a spaceship and, and then comes back and it looks like, the guy on Earth is aged 9.3 years, but the guy in the spaceship is only aged 4.1 years during that same journey. That's your twin paradox, or at least that's a big part of the twin paradox. Okay, now we also want to solve for the distance here. So in going back, we have to say, okay, well, who's proper distance or proper length? So, and things of that sort as well. And now it's not the guy in the spaceship for which we measure that. It's actually the guy on Earth. So he is at rest relative to Earth and Proxima Centauri's locations, the first half of the journey, and then same thing on the way back. And so it's him for which we define proper length or proper distance. And so in this case, we are going to solve for, we know his distance is the 8.4 light years. It's his we want to solve for to see this length contraction here. And so in this case, again, we've got L equals LP times the square root of 1 minus v squared over c squared. And so L is going to equal that 8.4 light years times the square root of 1 minus 0.9 c all squared over c squared. And again, the c's are going to cancel and be left with the square root of 1 minus 0.9 squared. And so in this case, 8.4 times the square root, parentheses, 1 minus 0.90 squared, and my parentheses. Oh, and I erred my syntax. So let's take a look at what I did wrong here. Oh, I put a comma in the middle somehow magically. We'll delete that. Try it again. 3.7 light years. All right, so there's the 3 answers we were looking for. So from his perspective, it's just 3.7 light years away, the total distance there and back, not the 8.4. That's your length contraction. All right, so one thing to note here. So we measure distance here. Sometimes people look at this length contraction, not so much as like the distance of a journey, but maybe as like the length, instead of the distance between 2 points like Earth and Proxima Centauri and then back, they might look at it as just the distance between the front of the spaceship and the back of the spaceship. So, and they look at this kind of a thing of length contraction, it would make it look like the spaceship actually shrunk. So, and was smaller in size. Now, one thing to note when you kind of take a look at it from this perspective, the length is only contracted in the direction of motion. And so if we did look at something like that for the spaceship would be getting shorter in this dimension, but its width in kind of this dimension would not change at all. It would not be measured any differently from any of those inertial frames. Okay, now the second part of this problem is really the same problem over again with a slightly different speed. So recalculate the time of flight and round trip distance from the perspective of an observer on the spaceship for a speed of 0.99 c. And so what I just want you to see here is what happens as we get closer and closer to the speed of light. So again, recalculate the time of flight and round trip distance from the perspective of an observer on the spaceship for a speed of 0.99 c. All right, so for the observer on the spaceship, that was the distance. So, and again, for the observer on the spaceship, it was the proper time here, this 4.1 years. And the only thing that's going to change here is that instead of 0.9 c, it's now going to be 0.99 c, both there and here. And that's what's going to change here. And so instead of 3.71 years, we're going to get a little bit different answer. In fact, I'll just write it below that right there. So, and this delta TP, the proper time, I'll write for the second part of this recalculation right below it as well. So I'll represent both sets of answers. And I just want you to see what happens to both of these as we get closer and closer to that speed of light. And so what's convenient is with my TI calculator, I can just hit second function entry, and I'll hit second function entry again and go back, and it takes and puts up this lovely calculation for me. No, not right there. One more time. There we go. 9.3 times the square root of 1 minus 0.90 squared. And I'll change that 0.90 to 0.99 and just hit enter. And it's all the way down now to 1.3 years. And 2 sig figs. And so the closer you get to the speed of light, the less and less time it appears to take as measured from the observer on there. So, and effectively you can envision that when you reach the speed of light, it takes no time. And you get some weird stuff. And then this is where people kind of speculate that if you could potentially go faster than the speed of light, then you could go back in time and things of this sort. So that's kind of where that comes from. Let's do the same calculation right here. So, and second function entry, and second function entry yet again. So that takes me back to this 8.4 times the square root of 1 minus 0.9 squared, and we'll change that to 0.99. So, and it takes me down to 1.2 light years. And so the distance gets even shorter and shorter as well. And so once again, as you get closer and closer to reaching that speed of light, the distance between 2 points gets shorter and shorter and shorter as well. And again, if you actually reach the speed of light, then somehow that implies the distance goes to 0. So, and again, this is just how the math works out. And again, everything we've seen with relativity is it's crazy, it's non-intuitive, it's very contrary to our everyday experience, and so are some of the results of these calculations, but that is exactly how it works. If you have found this lesson helpful, consider giving it a like. Happy studying.